All right, let's review the definition of a linear combination. We say a vector v is a linear combination of v1 through vn if we've built v by scaling vectors in this set and then summing those scaled versions. So in other words, v can be written as a scalar times the first vector plus a scalar times the second vector all the way up to the last vector, where these scalars are just real numbers. So it says here some of these vectors are scaled and added. If we didn't want to use a vector in our sum, we would just choose, we could either think of not using it or using it just where our scalar multiple is 0, so that would kill it. Okay, so next up, let's take a look at this in action. In this problem, we're going to show that the vector 1, 2, 3 is a linear combination of these three shown vectors. We're going to actually demonstrate how we write 1, 2, 3 as a linear combination of these vectors. So we're going to start just from the definition of one vector being a linear combination of a set of other vectors. So what we would like to do is to find A1, A2, and A3 in R so that the vector 1, 2, 3 is written as a sum of these three vectors where we've scaled by the factors A1, A2, and A3. All right, so I'm going to show you sort of a longer version, and then we'll see pretty quickly that we can shorten this. Okay, so I'm going to multiply these scalars into the vectors. So we've got A1, 0, and 3A3, 3A1 rather, plus 0, 2A2, 4A2, plus A3, A3, 2A3. And these sum to A1 plus A3, 2A2 plus A3, 3A1 plus 4A2 plus 2A3. And so we're left with the system 1 equals A1 plus A3, 2 equals 2A2 plus A3, 3 equals 3A1 plus 4A2 plus 2A3. Hey, that's a system of linear equations. And we know how to solve those. What do? We are going to put these guys into a matrix where our augmented column is 1, 2, 3. Okay, we're going to have an A1 column, so that's going to be 1, 0, 3, 0, 2, 4, 1, 1, 2. And we're going to augment by the vector 1, 2, 3. Notice these columns are the vectors. Okay. So we've taken the three vectors, that is the set we're drawing linear combinations from, and we're augmenting with the vector that we want to show is a linear combination of those three. All we're going to do is row reduce to find the unknowns A1, A2, and A3. So let's do that. Okay, we're going to row reduce this augmented matrix. Please feel free to pause as we're going. I know I'm going to pause to write in some of the work from going from step to step. So our first step is that we are going to take row 3 and we're going to subtract away 3 copies of row 1. Next, we are going to take away 2 copies of row 3 from row, we're going to do row 3 minus 2 copies of row 2. Okay, and then let's just change this pivot so that it's a 1 by scaling by negative 1/3. Okay, now we are time for some back substitution. So we're going to be clearing out all of the values above this pivot just by subtracting copies of row 3 from row 2 and row 1. We need to do this at the same time since it is not going to, we don't have any dependencies. The order of it doesn't matter. Okay, and last but not least, we're going to change this pivot of 2 to a 1 by scaling. So I'm going to scale row 2 by 1/2. All right, and so we arrive at the reduced row echelon form on the left. We've got the identity, and we can read off now our solutions. We've got A1 is equal to negative 1/3. A2 is equal to 1/3, and A3 is equal to 4/3. All right, we can easily check our answers if we calculate negative 1/3 times 103 plus 1/3 times 024 plus 4/3 times 112. So negative 1/3 times 1 plus 4/3 times 1 is going to be 1. Negative 1/3 times 0. So 1/3 times 2 plus 4/3 times 1. 2/3 plus 4/3 is 6/3 or 2. Negative 1/3 times 3 is negative 1. Oops, this one I'm going to write out. Negative 1 plus 4/3 plus 8/3. 4 plus 8 is 12/3, which is 4 minus 1 is 3. So we end up with 1, 2, 3. So indeed we have found our coefficients that show how to write 1, 2, 3 as a linear combination of these other 3 vectors. In this video, we're going to decide whether or not the vector 0, 0, 0 is a linear combination of these 3 shown vectors. We're going to start just with the definition of a linear combination. So we say that 0, 0, 0 is a linear combination of these 3 vectors if we can find scalars that make the equality true. Okay. Now, you may be able to sometimes guess scalars that work. In this case, you might take a guess at some that work, but we also have the option to solve it in a way that we solved the last problem. What we can do is put these guys as columns of a matrix where we augment with this vector. And what we're going to do is row reduce to see whether or not we get a consistent system. Moreover, so we know that if this is a consistent system, it is going to be a linear combination. We can find what those scalars are by doing the row reduction. the row reduction will show us how it's a linear combination. Okay, here we have a pretty straightforward row reduction. Because we have 0, 0, 0 here, we know that it will end up being consistent. Let me just run through what our row reduction ends up being. And I'm going to hide some of this row reduction because we've already row reduced the left-hand side. We know that it ends up just being the identity matrix. And on the right-hand side, all of these row reduction steps aren't changing the fact that we always have zeros here. So what do we end up with as our scalars? Here we can use scalars of 0, 0, and 0. So it is true that this vector is a linear combination of the others. In fact, this vector is included in every single set of linear combinations of these vectors. Whenever you have a set of vectors, the 0 vector can be written as a linear combination of that set. Let's look at one last example. Let's look at another example. So we want to know whether or not the vector 1, 2, 3 is a linear combination of these 3 new vectors. Okay, so we're going to go again to the definition. We're looking to see if there are scalars so that we can put in these scalars a1, a2, and a3 so that when we multiply in and add, we get 1, 2, 3. Now sometimes people have this feeling that you should be able to eyeball and figure out what a1, a2, and a3 are. And if they don't see an obvious choice for a1, a2, and a3, it's easy to say like, oh, maybe there's no scalars that will work. I want you to be really careful. This is not a good strategy. In general, we won't be able to eyeball values for a1, a2, and a3. You won't be able to look at it and say, oh, it's got to be this. That doesn't mean that there aren't solutions. What we need to do is put it into an augmented matrix and row reduce and see whether or not we have solutions. This row reduction will also tell you what those solutions are. Okay, so we're going to put these vectors into a matrix, and we augment with the vector that we're trying to decide whether or not it's a linear combination of the other 3 vectors. Okay, so to row reduce, I'm going to start by taking row 2 minus row 1 and row 3 minus row 1 minus 3 row 1. Okay, next up we're going to do row 3 minus row 2. And here we can see something interesting is going to happen because row 2 and row 3 are the same except for the augmented column. So we end up with a final row that we can interpret as follows. 0 times a1 plus 0 times a2 plus 0 times a3 is equal to -1. So 0 equals -1. This is inconsistent. What does that mean? It means there are no a1, a2, and a3 that make this equality true. So the vector 1, 2, 3 is not a linear combination of the others.